it's my pleasure to introduce Aydın Keser. Why? Okay. And Aydın is working in our group, and he is a theorist, and this is theoretical talk. But Aydın works very close with experiments, and his main projects so far have been hydrodynamics of electron. It's collaborative work with experiment, and this recent work, which is about Heisenberg-Euler action and Heisenberg-Euler effects in Dirac materials, it's very interesting theoretically, but it's also suggestions of several new experiments, and this is probably why this topic is mostly interesting. And yeah, that's probably all I should talk, because probably many of you know Aydın, and you don't need a personal introduction, but this is sort of scientific introduction. And Aydın, I pass it on you.
Well, I thank Alex Sushko for the kind introduction.
Aydın, can I just interrupt? Can I get you to put your video on?
Sure. My video is on it. You can't see me. Hello?
Your video is working on my screen.
Is it? Okay, good. Okay, it's me then. Hang on a minute. You keep going, Aydın. I'll work this out.
There's two Aydın Kesers though.
Oh, is there?
Yeah.
I'm connecting from phone for the video because I don't want to use the bandwidth and risk myself. It might crash if it's from the same device. Is everything all right? Can I start now?
Yeah, yep, fire away.
All right. I thank Alex Sushko again for the kind introduction. And I'm pretty sure most of you know me from the good old days when we used to hang out in in-person conferences and meetings. I'm glad to talk to you again. And this is a presentation of my recent work on nonlinear quantum electrodynamics in Dirac materials. I've given this talk briefly in the last year's Fleet annual meeting. I don't want to bore you too much. Today, I'm going to give more details on connections to recent experiments and possibly future experiments, proposals, and some accurate estimates of what we are doing in real materials. I've done this work with my supervisor in UNSW, Alex Sushko, and our Dr. Yuri Lian from Purdue University. Our work is on archive at the moment, and under review in physical review. Recently, we also contacted 2 Fleet experimental groups, and they kindly responded. The group for the growth and testing of Bismuth Antimony alloys, which will play a crucial role in testing our theory. And also, we contacted Jan Seidel for future possible collaboration on dielectric and magnetization measurements of these materials. If all goes well, we'll be able to test our theory, verify, or who knows, falsify it. Because the talk is called Nonlinear Quantum Electrodynamics, I'd like to start with linearity and see why it breaks down and why we need nonlinearity to begin with. It's easy to explain linearity by specific examples. For example, when you study circuits, you are introduced to some 2-terminal devices. For example, a resistance is a device that establishes a linear relationship between the voltage applied on the device and the current passes through it. Similarly, we have a device called an inductor, and there's a similar relationship between the magnetic flux in this device and the current that passes through it. And finally, you have something called a capacitor, which stores a charge that's linearly proportional to the voltage applied on the device. You can have multi-terminal linear devices. I conjured a quantum anomalous Hall device here, and this creates a transverse voltage when we apply, say, a current in X direction, and the proportionality constant contains the magnetization or the sign of it. In some cases, there's some saturation and nonlinear behavior, but for the time being, this is to illustrate that you can have arbitrary terminal linear devices which establish linear relationship between terminal voltages, currents, charges, and fluxes. So we can generalize this concept of linearity and apply it to a wide range of systems, and it has some far-reaching consequences. So let's make a very abstract definition of linearity. So a linear system, let's say a toaster, has an input, a slice of bread. You put one slice of bread and you get one toasted slice of bread out. So in a linear system, what happens when you put two slices of bread? Well, you get two slices of toasted bread. As simple as this is, it can be applied to many things. For example, you replace bread slice with electric magnetic field, circuit variables, as I just shown, light and electromagnetic waves. You can apply it to low amplitude water and sound waves. Newtonian gravity obeys this principle. Quantum states, fields, spinors, all obey this principle. And you can have, for example, a red, green, blue image matrix, and you can add these matrices like you do with bread slices. And digital signals in modern communication technology are processed using linear algorithms like FFT and convolution. When you study what kind of device runs these linear algorithms, you look into electronics. So you want to make hardware that can run these linear algorithms that process digital signals, let's say. And then when you study electronics, they show you something like this. Wait a minute, in a linear system, a linear two-terminal device, if you reverse the current, the voltage should simply switch sign, but the magnitude will be the same. This is not the case for a diode. This is the IV characteristic of the diode, and it has all sorts of nonlinear behavior. I'm not going to dwell too much on the operation of this device. I'm sure many of you know how it works, and possibly some of you are working way more advanced versions of this and making it in the lab anyways. And by far the most useful electronic component, probably of all times, is the transistor. Here's a MOSFET, and it also has a very nonlinear IV curve. Not only it is a diode, when this drain source voltage is reversed and it's positive, it has this linear and saturation regions depending on the applied gate source voltage. So the takeaway message from this introductory part is that electronics is nonlinear. This nonlinearity can be due to a composite device like PN junction and MOSFET, etc. It can also be due to intrinsic material property, such as the transport property in a material might be nonlinear. Today, I'm going to mostly concentrate on nonlinear magnetoelectric response. It has certain advantages because this type of response is immune to impurities. It can be a probe of quasi-particles, and it's a thermodynamic property. What do I mean by thermodynamic property is that it is related to the energy stored in the material. In a linear material, the energy stored due to electric and magnetic fields in the material is proportional to E squared, and it is a component that's proportional to B squared. But in a nonlinear magnetoelectric response material, the thermodynamic energy acquires a component, and this component contains higher powers of fields and nonlinear functions of it as well. So before going into nonlinear magnetoelectric response, I would like to say that the nonlinear transport phenomena are a hot topic at the moment. I'm showing you a bunch of very nice research papers that came out of recently. So this paper on the left bottom corner predicted that in a time reversal linear material, although the linear Hall effect must vanish due to Onsager relation, the nonlinear Hall effect can be non-zero due to baric arbitrary dipoles. And this has been observed in a tungsten telluride recently by Ma and company. You can see this Nature paper. And then there's also an anomalous version of it, like you apply an electric field in a material and it induces magnetization, and it creates anomalous Hall effect. Therefore, the anomalous Hall currents they depend non-linearly on the applied electric field. And finally, you can see this excellent review on how nonlinear topological systems can be used in photonics and future applications might include rectification, down conversion, up conversion, and all sorts of nonlinear optical processes. So let's go back to magnetoelectric systems, the magnetoelectric response. And both this transport and magnetoelectric response, mainly what I'm going to consider happens in Dirac materials. So let's see what I mean by Dirac materials. A material where you have low energy bands that are effectively described by the Dirac Hamiltonian, and they only have a number of small degrees of freedom, which is band velocity V and the gap 2 delta, let's say. And then there's also a cutoff beyond which the Dirac approximation breaks down or the band is terminated. So this linear dispersion comes about because of spin-orbit coupling, and this band can be zero, for example, in Dirac semimetals and Weil semimetals. It can be positive in a topologically trivial Dirac insulator. It can also be negative in topological insulators. Application of Dirac physics to materials is not new. Actually, Wolf already wrote down an effective Dirac equation for bismuth, electrons in bismuth in 1964. But recently, there's been a revolution in condensed matter physics due to their many interesting signatures, including transport and anomalous Hall effect and anomalous lambda levels, surface and edge states, and so forth. Today, I largely concentrate on large diamagnetic response and nonlinear magnetic susceptibilities of these materials. I here put a bunch of references that can get you started on these materials. One of these reviews are written by myself and Dimitri Kulcher from UNSW and our collaborators. So, as I introduce circuit elements to you, let's imagine a situation where we make circuit elements from a Dirac insulator rather than a normal insulator. So what we end up having is quite an extraordinary situation. For example, if you try to make a capacitor, take two plates and stick a Dirac insulator in between, you end up having a B-field tunable capacitor. This is because of the fact that the energy stored in a Dirac insulator has an E² component which gives you the linear capacitance. But it also has a nonlinear contribution that goes like E² times B. And this effect is extremely large. Similarly, if you try to make a capacitor from Dirac insulator, you end up having a nonlinear capacitor where the electric field changes the capacitance. This is due to the fact that there's a term in the energy that goes like e⁴. This effect is perturbatively small, so it's there. I'm just mentioning it, but I'm not going to dwell too much on it because there are much larger effects in other phenomena, such as nonlinear magnetic susceptibility. For example, if we made an inductor out of a Dirac insulator, because of this dependence on energy, you would have a nonlinear inductor, and this effect is large as well. And finally, magnetization of the Dirac material turns out to be modulated by the applied electric field. And just like B² times B type of energy creates this B field tunable capacitor, it also creates an E field tunable inductor. So let's go and try to make these devices and make some specific estimates. I'll start by the capacitor case. Let's first start with making an ordinary capacitor. So what you do is to take two plates and stick an insulator inside, and then you apply an electric field. It turns out that there's a polarization vector that develops in this material due to polarization of atoms, molecules, polarization of the crystals, atomic bonds, and possibly electron gas. And in most materials, which are linear and isotropic, this polarization vector is proportional to the applied electric field. And this proportionality constant is called the dielectric susceptibility. Dielectric susceptibility is related to the relative permittivity through this equation. And basically what you measure when you measure capacitance is this intrinsic property up to some geometric factor that involves the ratio of the area of the plates to the separation of the plates. And most of the time, the polarization of many of these constituents of the material to this capacitance is positive. Therefore, you get mostly positive numbers, almost always positive numbers when you take a look at the electric properties of materials. And this is a physical quantity that can have a huge range. It can be something like 1 in air, something like 10 in graphite and gallium arsenide, about 100, 400, 1000 range in topological insulators and Dirac materials, quite a large value in barium titanate, and a whopping dielectric constant in excess of 250,000 in this calcium copper titanium oxide, which you can probably make a battery out of. So it stores so much charge that you can run your car on. So what if you replace the normal insulator in this capacitor with a Dirac insulator? Well, let's do that. So these are our two plates, and this is our Dirac insulator. And then we find that if you apply magnetic fields to the system, then you end up having a capacitance that's sensitive to the applied magnetic field. To be specific, I'll take this material, the bismuth antimony alloy. Well, bismuth, you can say, is already a Dirac material, but it's a semi-metal, so it makes a really poor capacitor. Instead, we dope it with antimony and it becomes a topological insulator. It's a known fact. At 4%, the gap closes, and when you operate at a substitution ratio of 7%, you get a topological insulator with 3 Dirac cones. The gap of this material is about 15 milli-electron volt, so you shouldn't operate near these temperature and terahertz regions where the insulator breaks down. Well, if you take this realistic dimensions of a 1 millimeter square plate and the separation is alpha 1/10 of a millimeter, and you find that when the external magnetic field is 0, you should measure a capacitance of about 10 picofarads. Now, if you turn on magnetic field, let's say parallel magnetic field, for every Tesla applied, you get an improvement of capacitance of about 1 picofarad. So I get this extraordinary situation where I can increase the capacitance of the device up to 100% by applying this moderate magnetic field that is parallel to the electric field. Well, this effect is suppressed as you increase the gap quadratically. You can increase this effect if you use a Dirac material that has a higher band velocity. And of course, number of cones is more cones are better because every cone contributes similarly. Now let's take a look at inductance or magnetic susceptibility. Let's start with that. So if you try to make an inductor, let's say a coaxial cable, what you measure as inductance is basically this intrinsic quantity called the magnetic permeability up to some geometric factors, including the length of the cable and the logarithm of the outer radius. This intrinsic property called permeability relates to the magnetic susceptibility through this relation. And the susceptibility in a linear system relates how a magnetizing field creates, it relates the magnetizing field to the magnetization. So when you apply an external field of H, what happens is that core shells, electron spins, electron orbitals, they all get magnetized in response to this external field. And their contribution to magnetization can be both positive and negative. And we find that in Dirac systems, the valence band contributes significantly to this magnetization. So the total magnetic field contains the applied magnetizing field H and the magnetization. And roughly this quantity measures the ability to admit magnetic flux. For example, if you have a superconductor, which has a diamagnetic susceptibility of -1, the maximum possible value, it completely expels magnetic field because you add this thing and then it becomes 0. So if you apply a large magnetic field, external magnetic field, the superconductor, inside of the superconductor still has no magnetic field. And this is actually one of the defining properties of superconductor called the Meissner effect. In non-superconducting materials, diamagnetic susceptibility is a much weaker property. A champion among non-superconducting materials is bismuth, which is about -2 × 10⁻⁵ diamagnetic susceptibility, and it is a Dirac system, thanks to this huge valence band contribution. Sorry about that. Yeah. And you can also have paramagnetic materials. For example, iron has a very large paramagnetic susceptibility, which explains why you can easily magnetize iron. Well, let's try to make an inductor from a Dirac insulator. Well, Here is our inductor. So what we do is you have a current loop. When you pass some current, you create a magnetizing field. This magnetizing field magnetizes the sample. You can measure this magnetization by using a squid device, which is a superconducting quantum interference device, which is extremely sensitive to magnetic fields. Now we find that when you apply external electric field on top of the magnetic field, the magnetization that's registered by the squid should change. And this is a sizable effect. So let's give an example again. I'm going to take this material called Lepton Shellinite. This alloy structure is a topological insulator at about substitution ratio about 25%. The gap is 50 milli-electron volts. And then when you measure magnetization, it has this component that's independent of electric field. And we find that it also has an electric field dependent component. Bear in mind that you can't apply any electric field on the system because it has a finite gap. So you should avoid fields that are near this 10 kilovolts per centimeter. So what we predict is that if you increase electric field, you should observe a change in magnetization in the B field direction. And that should be proportional to the electric field, applied electric field squared. And this limiting value, 2.5 kilovolts per centimeter, is proportional to gap square of the material. And let's say if you apply this large electric field, the change in magnetization can be written as a function of the external field. And it first rises and saturates, and the saturation value is about 60 nanotesla at about 1.7 Tesla. And this effect is extremely anisotropic because if you change the field direction from parallel to the B field to perpendicular direction, the magnetization contribution of the electric field becomes negative and also makes this weird saturation and decay curve. And it can go up to minus 30 nanotesla at about 4 Tesla. Well, these numbers are easily observed. These type of magnetization easily observed in squid, but their absolute values can be quite small. It's a nanotesla versus Tesla here. You can slightly increase these numbers by taking a material that is a larger gap. Instead of Lepton Shellinite, if I take one of these Dirac insulator, topological insulator family members, the gap is about 200 milli-electron volt. And then this electric field induced magnetization can rise up to 1 microtesla here. And the advantage, one advantage is that because gap is larger, you are allowed to apply higher electric fields. But still, you see, the scales are very different here. So you have to be able to measure something between 1 nanotesla and 1 microtesla. And how do we do that? Probably experimentalists know this much better than I do, because we have an effect that's proportional to E squared. What you can do is to apply an electric field that has a kilohertz frequency, and then the output, the electric field modulated magnetization, by virtue of being proportional to E squared, should pop out at exactly twice the frequency of the electric field. And this power spectrum density, you have this very large DC component, the signal that we predict, and also have some noise. Thanks to the extreme sensitivity of squid, we predict that you can easily measure the signal. And finally, when you make an inductor out of a Dirac insulator, it turns out that magnetization, magnetic susceptibility, or inductance, however you call it, depends on the applied magnetic field. Again, if you take Bismuth antimony with gap 15 milli-electron volts, you predict that you will observe magnetization or diamagnetic susceptibility that goes like a function of applied external field. So we predict that at very small magnetic fields, you get the linear component of the diamagnetic susceptibility of Bismuth, which is about -2 × 10⁻⁵. And as you increase magnetic field, it first drops quadratically, and then if you go beyond this 5 millitesla, it drops logarithmically. So you can halve the diamagnetic susceptibility of the system by applying a field about 1 Tesla. So it's a very easy to measure effect. And a closely related effect is non-saturating magnetization. So again, you do the same setup, but instead of diamagnetic susceptibility, let's look at magnetization. And then we predict that this magnetization, ironically, becomes linear in the system. In band insulators, parabolic band systems, magnetization usually saturates due to the fact that lambda levels are spaced too much at high magnetic fields, and they get progressively ejected out of the bands. So you can't see any magnetization at very high magnetic field. But thanks to the Dirac valence band, Dirac dispersion, this saturation never happens. And up to extremely high fields, you see this linearly changing, like almost linearly, B log B type dependence of magnetization on the applied B field. And this is a detectable large effect, and it's also been seen in tantalum arsenide, which I'm going to talk shortly. Now, after introducing you to experimental aspects of our work and what to expect and how to make realistic experiments, I'd like to take a step back from material physics and take you to a historical story on how nonlinear electrons.
Could I have a question? Could I interrupt? So the lambda levels for Dirac particles have zero energy state.
Correct.
Is it important? Does it contribute or make anything special here?
Yes, it does contribute. So if you take, instead of insulator, if you take bismuth, for example, that level, the zeroth lambda level in the conduction band of bismuth contributes enormously. And then it first, the conduction band creates magnetization oscillations, and eventually you get some saturation behavior. And there are some papers that claim a phase transition in conduction band electrons. Basically, they say that this valence, so they say that this lowest lambda level can go through a ferromagnetic phase transition. So it can be important. In Dirac system, though, because of the valence, so there's nothing on the conduction band. Everything comes from valence band. And valence band has quite a large cutoff, like 1 or 2 electron volts. So unless you go to extremely large magnetic field, I don't know, some like 50, 60, 100 Tesla, you can never isolate that lowest lambda. It always comes with other lambda levels in the valence band. And what you see here is this aggregate effect of those lambda levels, not due to one lowest lambda level, but summation of energy of low lambda levels in the valence band that has logarithmic contribution to susceptibility.
Okay, thank you.
How do we get these results? So to motivate the theoretical developments that lead to these results, I want to make an interlude. And now I'm not going to talk about materials at all. I'm just going to talk about vacuum. Vacuum is something that you get when you get rid of everything. So let's say you go to the lab, you take a vacuum chamber, and then you get the air and everything out of this vacuum chamber. And voila, congratulations, you made a Dirac material. Actually, this is the first Dirac material that's been discovered. Dirac discovered it. This Dirac material called vacuum is quite hard to work with because it has a gap of about half mega electron volts, so hard to excite it. That's why when you look at it in the lab, it's like an inert thing, it's just nothing. And then the band velocity of this material is equal to the speed of light, and its cutoff is stupidly large, so it's almost infinity for experimental purposes. So when they talk about Dirac vacuum, they show you this complicated table of particles and stuff. But from a material scientist point of view, this is actually very simple to understand. So for example, these fermions shown here, electron, muon, tau, are nothing but bands with different mass gaps. Electron band is the lowest, muon, tau, and their charge bands. And they have these antiparticles or the valence bands. And just like Fermi C in materials, you have this Dirac C in the vacuum, Fermi level. of the vacuum sits here, and all these states underneath, the negative energy or anti-particle states, are filled. Now, this vacuum material concept is a tremendous development in physics. It's like inventing zero, you know. First, it's hard to understand how can zero be a number. So if zero giraffe atom, doesn't make any sense. But once you understand the concept, it's very powerful. Like vacuum. Vacuum, how can vacuum be a material? I mean, it's just nothing. But it solves a very important problem. So people discovered that there are electromagnetic waves in vacuum. And this uncomfortable question popped out. What kind of medium does this wave travel on? If you have water wave, it travels on water. If you have sound wave, it travels in air. What kind of medium do you have for this electromagnetic wave to travel? And the answer is that it travels on the vacuum material. So for example, if you shoot a laser, they say this laser is an electromagnetic wave, and it's like very pristine, you know, this very pristine guided wave propagating in this direction. So we can easily model this with this distributed element models. This is vacuum. This is actually vacuum representation of vacuum Maxwell equation. Vacuum means there are some distributed inductances and capacitors, and it acts like a transmission line. If you solve telegrapher's equation, you end up solving Maxwell equation and get these waves. And some unit system, these quantities are related to speed of light, and this transmission line, vacuum transmission line, quotes, has an impedance called impedance of vacuums, 377 ohms. Well, as I told you in the beginning of my talk, these circuit elements are linear inductance and capacitance. Therefore, we can add telegrapher signals or light, and it's linearly additive, like bread slices, we can add them. That's why they merely interfere when they go through each other. Otherwise, they don't interact, just pass through each other. It's called superposition principle. Well, let's take a look at the energy density stored in this so-called vacuum material. You will say, okay, there's this distributed capacitance and inductance, and then they are made of this vacuum material. I'm going to write the energy density as electric field square, contains magnetic field square, and also has a component that comes from the occupied levels. Well, you will argue that, well, I never see, okay, it might be a very large number, I don't care because it's there. I don't measure the differences when I change electric magnetic fields. So you can argue that we can just throw this out and we write this as the energy density of electromagnetic fields. However, quickly after Dirac wrote his famous equation, Heisenberg and Euler realized that, wait a second, they said, wait a second, okay, we have this vacuum component, electric field and magnetic field energy density. But then these states that are occupied, they also respond to external electric magnetic fields. So it's not like a constant. There's a constant component that you can throw out, but there's also a component that's changing when you apply electric magnetic fields. For example, if you apply magnetic field, they become lambda levels, and total energy of lambda level is different from total energy of plane waves. And they find that this additional energy density contains all sorts of nonlinear terms, extremely high power nonlinear terms. And they find that these nonlinear terms become comparable to the vacuum energy, to the classical energy at these fields, E star and B star. They find that this E star, B star are proportional to the gap square. And because this vacuum material has a very large gap, they turn out to be extremely large numbers. So this is the value of the electric field at which you would observe some sort of nonlinear effect. And so this is the value of like billions of Tesla where you could see some nonlinear effect in vacuum. Nevertheless, it is there though. So you can see this effect near neutron stars or recently in heavy ion collisions on Earth as well. So it's an artist's impression of neutron star. Probably some weird optical phenomena are happening if you could get near it and don't get crushed. Well, as I told in the beginning of the talk, you can have in Dirac system, you can have nonlinear inductors and capacitances. So by virtue of these contributions that Euler and Heisenberg contribute, now we can we can model the vacuum by these nonlinear elements. For example, our transmission line or something like this that represents vacuum Maxwell equation, and it gave rise to light waves that just pass through each other without interacting. Now you have to replace them by this nonlinear inductance and nonlinear capacitance. And if you try to solve the telegrapher's equation with nonlinear system, you end up seeing that you can have a situation like this. So you put two telegrapher signals, in this case, two light beams, and they can scatter because one of these guys change the capacitance and inductance on which the other is traveling. Well, lo and behold, this thing is, well, by the way, these things have terribly complicated names. So this guy here is called an effective action, and this guy we call a Feynman diagram, but they're really simple. Okay, this light by light scattering is observed. So what you do is to send two light beams, actually two lead atoms, and lead atoms contain a lot of photons swarming around them. And you make these photons squeezed in a bunch of lead beam, and then they can scatter, and then you get scattered light. And here's a picture that shows it. That was published by the Large Hadron Collider Atlas experiment. They actually saw that you can have this momentum conserving collision of light with a light. You can check this on this news article. Well, I calculated for fun what would be the collisional cross section of two light beams that are visible, and I get a stupidly small cross section. So if you have gazillions of watts, maybe you can observe unless you create a black hole or something. But because the cross section goes with 6th power of frequency for gamma rays, this becomes a realistic number. So the size of the atom, basically. If you squeeze light beams into this kind of diameter, you can see this light by light scattering as shown in the LHC experiments. Now, what I showed you is that there's this high energy theory that has some observable consequence due to nonlinearity, and this vacuum material, the QED, quantum electrodynamics, is extremely similar to Dirac material. All you have to change is the velocity of the fermion, its cutoff, and the gap. Otherwise, the whole theory goes as is. And by using this analogy, you can predict a number of interesting effects, like anisotropic nonlinear dielectric behavior, electric field tunable magnetization, and magnetic field tunable capacitance. And there are also some already observed behavior that's related to this phenomenon. For example, the non-saturating magnetization, tantalum arsenide, and diamagnetism. So this is the end of my interlude on vacuum quantum electrodynamics, or vacuum material, however you call it. I'll go back to material physics and go over our experimental suggestions in the light of this theory. So what do we need to have? We need to have a 3D Dirac material or topological insulator. The more cones, the better, because every cone contributes. Tantalum arsenide has 6 pairs, Bismuth has 3 Dirac cones, Lepton Shellinite has 4. Band should be linear up to 1 to 2 electron volt, because you want to have a sizable range where this Dirac Hamiltonian is applicable. The gap shouldn't be very large, because when it's very large, then when it gets close to this cutoff, and the applicability region of Dirac Hamiltonian is destroyed. It gets very narrow. And also, when you increase this gap, even though you increase the cutoff with the gap, then the fields at which nonlinear phenomena occur increase quadratically with the gap. So you don't want very large gaps. You don't want very small gap either, because in that case, if you do an electrical measurement, you can easily break that gap. So 10 to 100 millielectron volts is good, and it's also reasonable. We have a bunch of gate tunable systems where you can achieve these numbers. And also, of course, if you say that I'm going to do only magnetic measurement, you can do it on coil and Dirac semi-metals, and the gap can be 0. And band velocity should be large, and DC dielectric constant should be about 100. Otherwise, you run into some theoretical problems due to electron-electron interaction. The material can be arbitrarily anisotropic. Our theory can capture this. What we do is to take this geometric mean of velocities in 3 different principal directions, and then take this geometrically average velocity. And then this anisotropy matrix pop out here and there. Otherwise, the theory is still, theory goes as is. Well, let's start with experiments that do not involve electric field, only magnetic field. So the linear component that we predict from Dirac theory is equal to this. So this is the linear diamagnetic susceptibility of the Dirac system. Alpha is a universal constant called the fine structure constant. It's about 1/137 or 0.01. As I said, V is the band velocity. And this was already known. You can check this review by Freya. We also find that there are nonlinear contributions, and if you include nonlinear contributions, you can get this realistic number that agrees with experiments. And because bismuth is semi-metallic, you can, as I talked in response to Dimitri's question, I mentioned that you have all sorts of oscillations due to Fermi pockets. It's better to avoid them and use this insulator as bismuth antimony alloy. If you use this instead of bismuth, you should get a very clean diamagnetic susceptibility as a function of applied magnetic field. You can basically halve, as I said, the susceptibility by applying 1 Tesla. And coming to magnetization, again, a zero electric field experiment. In small gap and gapless systems, you find that magnetization can be given by this rather simple expression, where this is the cutoff with 1-2 electron volt. This is applied magnetic field, and this is the anisotropy matrix again. And the estimates I give here is like that. Really, only the numbers change, but the universal behavior shouldn't change. So I did the same calculation with tantalum arsenide, and this guy is observed. So I'm going to show you this experiment now. So this is what they observed. In this experiment, not only they do a squid measurement to measure the parallel component of magnetization, they also use this cantilever technique to measure transverse component, where an applied magnetic field that's oblique to this plane creates a magnetization in the transverse axis, which creates a torque and depresses the cantilever. And from capacitance measurement, you can measure this effect. And they get this really good agreement with theory and experiment. So what's new? You can say that, look, all I have to do is to, if there's no electric field, I just sum lambda level energies like they did in this experiment. And here are the lambda level energies. And then I calculate it. So what's new about it? So basically, when you turn on electric field, and when you try to look at these magnetic field tunable capacitor and electric field tunable magnetization, you need to turn on electric field. And once you do that, this procedure of naive summation of lambda level energies do not work. So what we do is to go back to 1935 and carefully analyze what Heisenberg and Euler did, and then apply this under this philosophy to materials. And once we do it, for example, you obtain this expression in the strong magnetic field limit. Here I give a quantity that's closely related to energy density. The difference is only mathematical, so don't worry about it. Something like energy density called Lagrangian density. And it's written in terms of this normalized field, and normalized fields are basically the ratio of applied fields to these critical fields, and critical fields basically they depend on gap square. So this theory can be applied both to vacuum, like in LHC experiment, or material. The only difference is that the velocity of fermion is different. It's much smaller in Dirac material. Compton wavelength is much larger in Dirac material. The gap is much smaller in Dirac material. Well, we have anisotropy in Dirac material, vacuum is isotropic. And you have this extreme difference in critical fields. So whereas you need extremely large magnetic and electric fields to observe nonlinear effects in ordinary vacuum, we can see them in much smaller moderate fields. And this is our contribution. So for example, for E field modulated magnetization, from the above energy density, we get this simple formula. And then once you run this experiment, you get these numbers from this formula. So this energy density and this formula explains the gap square behavior of these limiting values that I showed you in the beginning of my talk. Once again, your magnetization that's an additional magnetization that's proportional to electric field square, and at electric fields about 2.5 kilovolts per centimeter, this magnetization can be drawn versus the applied magnetic field, and it saturates about 1.7 Tesla, and then it's very, very anisotropic, depending on the direction of the applied electric field. And then by far the largest effect we predict is this E field tunable Dirac capacitor. And from energy density, we get a simple formula like this. If you apply it to bismuth antimony, as I showed in the beginning of my talk, you get a base capacitance of 10 picofarad and 1 picofarad for every applied Tesla in the parallel direction. I can get 100% enhanced of capacitance as a function of a parallel magnetic field. And due to this nature of this formula, you can get this inverse dependent square of that and number of cones and velocity of the fermion. I'm going to put the conclusions here in the form of this conceptual map again. So we've considered Dirac materials and their magnetoelectric response. In analogy with actual vacuum, we find that this magnetoelectric response must be very nonlinear, and these nonlinear effects can be seen in a number of Dirac and topological insulators, and they can manifest themselves as magnetic field tunable capacitor, electric field tunable magnetization, anisotropic and nonlinear behavior, nonlinear diamagnetic susceptibility in small gap systems. Well, thank you very much for listening to me. Please let me know if you have any questions. And of course, if you're interested, don't forget to check out our archive submission, which has this following code. Thanks a lot.
Oleg, did you want to, what would you call it, monitor any questions?
Okay, for sure. Any questions?
Michael did put something in the chat, but he'll have to interpret it.
Yeah, we were having a little side discussion. I think sodium-3 bismuth fulfills some of these requirements for looking at the magnetic field effects. It's Dirac-like over a very large range of energies, has a very high velocity, high dielectric constant.
Effect would you like to talk about so I can?
Is it 3D, Michael?
It's 3D.
Ah, interesting. Somehow, well, okay. Clearly, I had a wrong imprint in my mind.
What material?
Yeah, we've been working on the 2D version, but
No, I understand why I have this imprint.
yeah. I'll send you a reference.
Interesting. Okay, more questions or comments?
I have a question. So you discussed nonlinear in magnetic field, but what about nonlinearity both? So the term proportional to the E and B at the same time, to the, for example, scalar product.
Very good question.
The-
We have a term in this energy density that goes like E dot B. And this guy does not give you a nonlinear response. What it gives you is topological magnetoelectric effect. So what you have is, for example, you apply electric field, and then that creates a magnetization. And if you have a magnetic field, you create polarization. But it's not nonlinear response. So you cannot create nonlinear diamagnetic susceptibility or nonlinear dielectric constant, simply because if you take derivative with respect to electric field twice, that term vanishes. Well, these nonlinear effects we describe are independent of whether the gap is positive, negative, or whether the insulator is topological or non-topological. But in addition to nonlinear effects we describe in topological insulator, yes, you have to include that E dot B term.
Okay, thank you.
Sure.
More questions? Or comments?
Doesn't seem to be. It's any. Do we want to wrap it up then, Oleg?
Yeah, if there are no more questions, okay, just let us thank Aiden for very interesting talk. And yeah, and so then happy Easter, right?
Exactly, yes. No lockdowns. We can go away.
Okay.
Thank you
Aiden,
very much,
really
Aiden.
great talk. Thank you.
Thank you very much. Thanks for listening and enjoy the holiday.
You too, Aiden. Thank you.
Stay safe. Bye.